Hello class, this is a continuation on the proof of axioms and theorems. In the previous video, we've just proved that the angle sum of a triangle is 180 degrees. I've also shown how we could understand axioms first and use axioms to make a proof. I'm going to continue this. I'm going to continually use this proof, but I'm going to build on top of it using other axioms. Now, the tricky part with this is that there are axioms that aren't shown here, but these axioms are taken from algebra and number theorem. So you'll just have to work with me here and understand that there are many axioms that we use without even realizing it. So the next theorem I'm going to prove is that the number of diagonals in an n-sided polygon from one vertex is n minus 3. The first thing we need to understand is what a diagonal is. A diagonal is a line connecting non-consecutive vertices in a polygon. So a polygon has, this square has 4 vertices, 1, 2, 3, 4. Consecutive vertices are simply just those that are in a row. So 1, 2, and 3. These 3 vertices are consecutive. So a diagonal is from one vertex to another vertex that is not consecutive. For example, this is not a diagonal. The diagonal from this vertex is this diagonal here. Likewise, the diagonal from this one is this one. So the diagonal from here, there are 2, 1, 2. The diagonal from here is 2, 1, 2. I'm sure you get the idea. The diagonal from here is 1, 2, and so on. And for this one, I'll just draw all the diagonals. See if I miss any. 1 here, 1 here, and I'm pretty sure that's all of them. So those are all the diagonals. Now, what we're looking at here is diagonals only from one vertex. So in this last example, I drew all the diagonals, but for now, in this proof, in this theorem, I only want to draw diagonals from one vertex. So let's take a look at the pattern that happens when we do this. So let's take a look at the shape. Well, with a triangle that has 3 sides, if we try and draw a diagonal from here, well, there aren't any, because that's an edge and that's an edge. There are no non-consecutive vertices in the triangle. So the number of diagonals from one point in a triangle is 0. I've made a quadrilateral here, so take a look. 1, 2, 3, 4. And I've already drawn in the one diagonal from that one point. So if there are 4 sides or 4 corners, vertices, there is one diagonal from that one point. A pentagon has 5 sides or 5 vertices. 1, 2, 3, 4. Whoops, sorry, hang on. 1, 2, 3, 4, 5. And if we draw the diagonals from this point, there are 2. Likewise, this is a hexagon, 6 sides. 1, 2, 3, 4, 5, 6. And if we draw all the diagonals from this point, there are 3. 1, 2, 3. Now, if we just follow the pattern, if we take away 3, we get 0. Take away 3, we get 1. Take away 3, we get 2. Take away 3, we get 3. So this is a proof that shows that this theorem, that the diagonals of an n-sided polygon, so it doesn't matter how many sides there are, if we want to count the number of diagonals from one vertex, we just subtract 3 from the number of sides. Interestingly, from this is a corollary, meaning a smaller proof that quickly results from this. So the number of triangles from the diagonals from one vertex, n sides of an n-sided polygon, is actually n minus 2. So from these constructions, I want you just to simply count how many triangles are there. So from here, there's 1. From this diagonal, we can see that there are 2 triangles. From these 2 diagonals, there are 3 triangles. And from these 3 diagonals, from that 1 point, there are 4 triangles. If we follow the pattern, n is 3, so take away 2. There are 1 triangle. Minus 2, 2 triangles. Whoops. Minus 2, 3 triangles. Minus 2, 4 triangles. So a nice quick proof to show that from this theorem, the number of triangles that are constructed are n minus 2. Now I'm going to use the last theorem, well, multiple theorems now. The previous theorem is that the angle sum of a triangle is 180 degrees. So applying that theorem, each of these triangles must all have an angle sum of 180. Now, applying the previous axiom that adjacent angles must add, if we look back down here, if we take a look, these 2 angles are adjacent, so they must add. These 2 angles are adjacent, so they must add. We continue this for all the angles, and you can see that all of these angles are the interior angle of this hexagon. But because that the angle sum of each triangle is 180, and these are all constructed with triangles, the angle sum of any polygon must be the number of triangles inside the shape multiplied by the angle sum of the triangle, which is 180. So I hope you can see how this theorem was constructed by multiple axioms. This theorem was constructed using patterns. That in of itself requires a different axiom. I'm not going to show that here. A corollary was resulted from this theorem. And this final theorem was a result of the previous corollary and the previous axiom shown here. So I hope that gave you a deep insight into the nature of mathematics and how a lot of mathematics is essentially just axioms and theorems interacting with one another to prove ideas that we initially just accept as truth, but as you can see, things require a certain proof. So I hope to see you in the next video, and best of luck.